listening to Worth Electronics' What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Worth Electronic technical specialists who are going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics' What's Up podcast. Today's podcast comes directly from a recent webinar presented by Worth Electronics' own Jelio Andreev. Jelio is a product manager in the optoelectronics area of Worth Electronic and is one of our go-to technology experts on the subject. Today, Jelio will dive into the basics of infrared lighting and then cover everything from data transfer to biometrics. You'll gain an understanding on the difference between infrared LED and other LED technology and when and how to use photodetectors in your design. He will also explain how to match the emitter and detector, and then finish off with real-life application examples. Enjoy this presentation of Infrared Revealed with Jelio Andreev.
I will start now with a short overview of the topic for today. We will start with the basic infrared LED introduction and what infrared LEDs are, the electro-optical properties, and posing and switching. Then I will go further with some photodetector basic information. What is a photodetector? What is the difference between a diode and transistor? And then after a short overview of matching an infrared emitter and detector, I would like to finish with some application examples of that we developed in our lab. So first, let's talk about what is an infrared LED, or what is the best component of an infrared LED. You can see a small sketch of an infrared LED. The main components are the housing or the package, the encapsulation, the gold contacts or the contact into a PCB, and the die. So when we have all this together, then we can put it into a single package and get an infrared LED. Excuse me. The main ingredient to make also the perfect LED is also to put the correct parts together so that you have the optimum output of your pre-selected chip. You have a nice encapsulation so the light comes out, and most importantly also for the customer, important to have the correct package. All this we will go through now in the following pages. First of all, the infrared LED or the pre-selected chip or die. We use in our production two different wavelengths of 850 and 940 nanometers dies for the two main emitting wavelengths of infrared. The infrared can also be identified with this 850 and 940 nanometer with two different wavelength parameters, the peak and centroid wavelength. In the photo you can see the peak wavelength is the peak of the maximum emission, or where the power, the emitted power, is the maximum. The centroid wavelength on the other side is more or less a quality of the infrared LEDs that can be defined also as how our detector perceives the infrared light. Actually, the centroid wavelength gives the middle part of the emission spectrum. So on the left and on the right side, the energy that consists into the peak has the same value, and the centroid wavelength just divides the spectrum in two energetically equal parts. What's important also to know about the infrared LEDs and the chips, as we are now talking about invisible light, we don't use anymore the standard values of lumen and candela, and we define our LEDs through the radiant parameters. This is the milliwatt or the milliwatt per steradian, which we measure in our lab following the CIE norm. And due to the high variety of chips and packages, we can offer different power output ranging from 1 milliwatt per steradian up to 100 milliwatt per steradian. This also would depend a lot on the viewing angle of the product and not only the chip. Of course, in our portfolio, we also have the high power LEDs with radiant intensity more than 300 milliwatt per steradian. But what is now important, except the chip, as I said, is the viewing angle. The viewing angle is given by the right encapsulation. You will find in our portfolio a lot of different lenses or encapsulations with flat lens or radial lens that give a different viewing angle. The viewing angle is the parameter that can show you, okay, where my light or infrared emission is going. Do I have a bright viewing angle, a broad angle, so I can illuminate at a short distance a very large area? Or do I have a narrow viewing angle? Or in other words, if I can use my emitter to shine on a very lengthy distance, but in this case also shining over or illuminating, irradiating more or less a very narrow area. As you can see, the dark blue curve of a very high emission viewing angle, we have a very high illumination. In our case, our products, we can provide a viewing angle products from 20 to 150 degrees, depending on the application that you have, if it's a short range, wide angle, or long range application. Another important parameter about the encapsulation is, of course, that it should not be absorbing. That's why we use special silicones that are transparent in the infrared range. So we have almost 100% of the light that is emitted from the chip to be exit out and to be used. Now, I would like to finish up the topic about the composition of the LEDs and come up later, and then turn our attention to two of the most important parameters. One of them is the switching of the LEDs. In this case, we are talking about the infrared LEDs. Those are light emitting diodes that have an invisible spectrum. So, and basically they differ a lot with LEDs that we use for signaling or indicators or general lighting. The most properties of the most important parameters, or why we use these LEDs, is we shine on something or we detect something. When we are using detection, then it's also important that we can basically don't need the LED to work all the time. We can use the LED in so-called pulse mode. In order to use pulse mode, we need to have a very nice rise and fall time. Usually, our LEDs have a very high switching frequency, which is in the range of around 10 nanoseconds, which converted in frequencies around 100 megahertz. the most important parameters in this case that define these switching times, or why an LED has a switching time. This is the parasitic and junction capacitance of the LED and the parasitic resistance of the whole package. If you can remember, this is why we use a gold contact, because we can have a lot better solderability on the PCB and then thus reduce some of the parasitic resistance that we brought in our designs or schematics. Another way to reduce the switching time is the capacitance. We use pre-selected chip and dies with a low capacitance so that we can have a very low switching times. Usually the switching times is measured between 0 and 100%, 10 or 90%, and 80 and 20%. Those parameters can give a lot different times. By us in Virtual Electronic, we use the typical rise and fall time of 10 to 90%, which you can see on the second graph. This is a lot more accurate for people that want to use the LED for a full off and full on state compared to the 20-80% measurement. This is why we give this value in our case. Except for the switching of the LEDs, important is that we are able also to pulse the LEDs. Pulsing the LEDs means that we can basically go above the continuous current and basically use short pulses to extend the output power or the range of our LEDs even higher, even more than what we have. You can see here a short graph of a pulse capability measurement for our LEDs, for our high power LEDs. This is basically done in a standard thermal chamber following JEDEC 51 standard. What we need to say here is, yes, it's possible to pulse your LED with a higher current than the available continuous current. Why is this possible? Because we refer to the different pulse parameters as explained, as shown above the graph. We have a duty cycle, on time and off time. And in the off time, an LED uses off time, or the chip uses the off time to cool down and to regenerate itself so it doesn't break. Because if we see a standard chip of 8 by 8 mil or 0.05 square millimeter, if we drive it with 0.7 ampere, then we will have, with a forward voltage of around 2 volt, we will have around 1 watt already into the LED. So this means that we will have around 1 watt per 0.05 millimeter square. If we convert this into watt per centimeter square, then we will reach even more heat generation than a standard oven in our house. In this case, we really need to implement a duty cycle to be able to run the LED in higher currents. As you can see from the curve, for example, if we have a pulsing time of 1 milliseconds or 1 e minus 0.3, then depending on the duty cycle, we can have different properties. For example, if we use a duty cycle of 50% or 50% on, 50% off time, then we see that we can reach probably around 75% higher than our standard current. But if you reduce the duty cycle to 20%, then we see that we can have around 300% more current than the standard current that we use for continuous, and so on, going on until we can reach a border limit where we can also damage the LED. This allowed post current depends also on the duty cycle, but it also depends on the chip size and the packaging. So how fast the LED can cool down or turn off. If you need further information about this and how our LEDs are driven, then please contact us at the emails given later so we can discuss it further. Now I would like to go on further and present to you the photodetectors. What are photodetectors? Yeah, of course, now we have an infrared emitter, a light source that emits a light that is not acceptable, not perceivable from human eye, the 850 or 940 nanometers. We still need some way to detect this data, to detect this light, or to get the signal that we are emitting. Then there are two different options. We can have a detector in the form of a photodiode or a phototransistor. There is a main difference of what is a photodiode and a photodetector. I guess each one of you knows what is a diode. So a photodiode would be the same as a diode, having an anode and a cathode, and generate current by light falling on it. The difference between a phototransistor here, a phototransistor is like a normal transistors where we have the base controlled by our light source. So the main difference between a diode and a transistor here will be the current that is generated. A diode will have a photocurrent generated in microamperes because we have just a simple conversion of light into electrons. A phototransistor on the other side has a collector current in milliampere. It means that here the transistor will work again as a transistor and we have a lot of gain. This means that our photocurrent will be multiplied and we'll have a stronger signal, and this means signal to noise ratio. The other main difference between the photodiode and phototransistor is also the response time or the switching time. A photodiode, because of the direct transition or direct conversion of light into electricity, have a very short switching time in nanoseconds. On the other side, a phototransistor, which has a gain and the current is, or the photocurrent is not directly converted from the light coming out, have a lot lower switching time in microseconds. But of course, this lower switching times is compensated by the better collection or the better sensitivity of a phototransistor. So this is, yeah, the main difference when we decide, okay, what type of emitter I need to use with my light. Do I need something fast and I have a very low signal to noise ratio, or I need a transistor that will improve my signal to noise ratio and sensitivity, and for example, I don't need it in a very good reaction time, or a reaction time in microseconds will still work for me. Another option to choose between the emitters, this is important, and it's both for transistor and for diode. Where do I put my emitter, or where do I perceive my light? So if we have diode that is somewhere outside in the sun or in a very well illuminated room, I will have a lot of noise coming out from my surrounding light. In this case, I would consider making my emitter or my detector use a detector with a daylight blocking filter as below. As you can see, in this case, a daylight blocking filter will just block all the light between 700 nanometers, or this is more or less the border of the visible range of the visible light. So my emitter will have a more stable signal and less noise that is coming from the ambient light. In our case, our products are available with and without daylight filter. And then this is, excuse me, this is now how I would define our perfect match. When we have an emitter or a detector, and then if we need something that is working and is not that is working somewhere that we don't care about the ambient light, then 850 nanometer emitter can be very well coupled with a detector without a daylight filter. Then we have almost 59% of sensitivity of the photodetector. And in case we have a very sensitive area, or we need to be very, very sensitive and get a very high signal to noise ratio, then our suggestion would be to go to a 940 nanometer emitter combined with a daylight filter detector. Then we are in the range where our emitter and detector have 100% match in the maximum sensitivity. What further we can suggest you, if you have to pair your emitter and detector, we have the same package and the same footprint for each emitter and detector, and they can be very well chosen from our database. You can find all our products in our online catalog. As you can see on the left side, the infrared emitter with the different sizes and forms and the different viewing angles. And on the right side, we have the emitter and detector with the correct size and form, of course. And if you need to test your product first and do some experimenting in the lab, don't forget you can also get the infrared LED design kit, which is full with all the different sizes and forms, and it offers a free lifetime review of the products. If you need this, you can always contact your local representative to ask for some more information about the infrared design kit. Now, after I have the introduction of the product, I would like to turn your attention to some of our applications, which we also tried in our lab, and we can discuss them in details if you need at later points. But yeah, as you can see, the main applications where we can use our emitters are the automatic switches for touchless hygiene systems, security cameras, light barriers and automatic doors, different touchless screens, biometrics, and different home appliance where the ambient recognition system need to work. One of the first applications that we did in our lab was to make a non-invasive oxygen measurement tool, or basically we built a biometric or pulse meter based on oximetry. How did this work? We just have an LED and a detector on both sides or on one side aimed at our vein, and the infrared light then gets reflected from the hemoglobin in our blood vessels, and then with the human pulse we are changing the reflection or the hemoglobin concentration. So each pulse can basically be tested with a different with the detector. To do this, we just put our emitter and detector, uh, and then we built a low pass and high pass filter and an amplifier and connected them with a microprocessor so we can get the results. And as you can see here, we have a very nice diagram of the systolic and the diastolic blood flow, or the inflow and outflow of the blood. So basically the distance or the period uh, given on the spectrometer is one pulse or one heart pump in each case. So in this case, with just 10 components from our catalog, we're able to convert the first or a very simple pulse measurement device. On this, we have also written an application note, and we have some interesting reference design which can be found on our website. What other applications we are now developing is data transfer. It's a lot easier to have a data transfer between an emitter and detector. If you consider the most simple one, this is a remote control where I can press a button and a signal would be sent with invisible light to my TV or my stereo, and then the program will be turned on and off, the volume will be turned on and off. If we consider that the switching time is up to 100 megahertz, then we can use this in even more complicated applications. The benefit of this data transfer is that compared to radio frequency, our infrared signals are easier to use. There are no radiation restrictions at all at the moment, and the bandwidth, the spectrum that we have here is a lot broader than the radio frequency. Response time compared to radio frequency is also with the speed of light, and basically the benefit and the drawback in this case, it's a very secure connection that needs a direct contact between emitter and detector. So without direct contact, there will be no signal transfer. What other applications are the different detectors, transmissive or reflective detectors, as you can see here. In a transmissive detector, we can think about different light barriers that can be used for different security zones. When there is a signal between, or when there is nothing between the emitter and detector, they create something like a light barrier. If something crosses this light barrier or there is an interruption of the signal, then a distress signal or a red lamp can say, no, there is something that is passing through, so I need to shut down. ERs can be used in this case for a short range and long range application to cover big areas. What other applications here are the reflective detection. For example, if we get a smoke detector, so we have some kind of radiation, and as we know, smoke will convert or will reflect light into a different angle. So if there is smoke, we can detect it with infrared light and change of reflective signal. Further applications include license plates, recognition, automated doors, and so on. With this, I would like to finish up my summary and summarize my talk. We covered the information about what are different infrared emitters and detectors. And based on the application, I guess everybody of you can find the correct footprint, the correct viewing angle, and the correct power output of our infrared LEDs and the matching photodiode on phototransistor based on the application. And depending on the field of applications, if you have any further questions, please contact us or your local sales representative so we can answer your corrections.
This podcast was taken from an updated Worth Electronic webinar. To view the materials and replay the webinar on demand, visit www.we-online.com/webinars or click the link attached in this podcast. You can also download the complete LED application guide at we-online.com/appnotes. You're listening to Worth Electronics What's Up Radio Podcast, where each week we are seeing what's up in the world of electronics and PCB design. We're checking in with leading industry experts and Worth Electronic technical specialists who will shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up Podcast.